Hello there. In this lesson, we're going to learn about the sun, the nearest star to Earth. We're going to learn some things about it that might make you think twice about looking up in the sky and seeing this happy ball that provides life to everything on the planet. It is also a very scary place where there's a lot of dangerous radiation and heat and ejected plasma and gases. So we're going to learn about some of the different features that scientists have discovered about the sun and why you probably don't want to go there. It's a good thing to stay here on Earth where we're kind of protected. So the sun is a big ball of gas, mostly hydrogen, and it undergoes a big nuclear reaction. And that's why we can see it, because of all the radiation that's being given off by that reaction. Scientists have learned by looking at the energy that comes off the sun and some physics to work out what's likely happening inside the sun, that there are layers. There are places where the gases behave differently at various distances from the surface. So we're going to learn about these layers, kind of like an onion has layers, right? You got this center part that will have different features as you go out. So that's what we're going to learn about, starting from the center, which we call the core. So the core, right here in the middle, that's where all of the nuclear reaction takes place. The nuclear reaction is one where the nucleus of hydrogen atoms is mashed together under massive temperature and pressure to produce helium. And so because you're changing the nucleus of one element into another, that is a nuclear reaction. So it's super, super hot there, like mind-bogglingly hot, about 15 million degrees, which is just impossible to imagine. I have no idea how to put that in any type of context. But yeah, just bad news for anything alive. You wouldn't be able to survive there. The next layer out is called the radiative zone. So radiative zone. And so this one's very descriptive in that radiation is exactly what is given off by that big nuclear reaction here in the core. And that energy from that reaction has to make its way to the surface. But you remember, all this gravity is like mashing everything down in this super compact blob of hydrogen to cause that nuclear reaction. So it's hard for the energy from the reaction to actually find its way through because of how dense it is and how much gravity is pushing the other direction. So this process is really slow as this energy gets transferred from atom to atom as it finds its way eventually through this whole zone and out to the next layer. It can take millions of years for the energy that was produced in the core to actually just make it out of that radiative zone. After the radiative zone, we get the convective zone. Oh, I need a different color that stands out here. Convective zone. So after the energy photons ping pong around in the radiative zone for a long time, it'll reach the convective zone. And I don't know if you've seen convection before with in some of your other science classes, but convection is how fluids move due to density. So when fluids like gases or liquids are hotter, they'll become less dense and they will rise, right? They'll go against gravity. And then when fluids are cooler, they'll become more dense and they'll sink. And so you get this cycling effect going around and around. And say if you boil water on your stove, there'll be hottest at the bottom, and so that heated water will rise up and the cool water at the top will sink down, and around it'll go until eventually all of the water in the pot reaches the boiling point. So the energy travels through this zone a lot more quickly because the gases are moving. Some are going up, some are going down, and so the cool gases will pick up energy when they get close to the radiative zone there and deliver it to the surface of the sun a lot more rapidly. All right, that brings us to the surface. the surface is the part of the sun that we can see. Of course, it's all gases, so there isn't a surface in that way. You can't, obviously can't stand on it for a lot of reasons, but it's not 15 million degrees Celsius anymore, though. It's cooled quite a bit. And that surface that can be observed with a light telescope kind of looks like, again, boiling water. Only instead of water, it's these turbulent gas blobs that are going up and down as they are bringing hot gas to the surface and cooler gases are sinking below. You can also see when you look at the surface of the sun that there are places that are relatively dark. They're darker than other spots on the surface. And so if you have a good telescope, you might be able to pick out a few sunspots and see that over time the sun is also rotating on its axis. And you can see those spots move over time. That shows you the movement, the rotation of the sun. So yeah, a surface kind of like boiling liquid, and a cooler place at the surface compared to other places in the sun. Cool being, 6,000 degrees Celsius, and then the darker spots are even cooler than that. Oh, a balmy 3,500 degrees Celsius, and that causes them to stand out. It's fluctuations in the magnetic field of the sun that causes these cooler spots and produces, this darker spots that we can see from the Earth. All right, so another feature that can be observed from the Earth is that there are places, often near where these cool spots are, where there are little explosions, like little pops at the surface. And so these are called solar flares. These little explosions will give out a bunch of gases all at once, sort of spewing them out into space. Just sort of rapid little pops. The other thing that you'll see, and you can kind of see it in this X-ray picture of the sun, there are these spots where there are these big arcing jets of gas that go out into space. So the big arcing jets of gas that go way out into space, those are called prominences. So a prominence is a big jet of gas, and be like millions of kilometers up and down there. Remember that the sun is massive, right? Many Earths, millions of Earths go into the volume of the sun, and of course at the surface you could think maybe 5 or 6 or a dozen Earths could be underneath one of these large prominences that go millions of kilometers out into space. So you got a flare, which are like an explosion, and a prominence, which are like a big geyser of gases that goes out into space. All right, the atmosphere that isn't exploding and prominencing, or dark spots that aren't cooler and have irregular magnetic fields around them. There's this two-layered atmosphere that doesn't glow as brightly as the surface of the sun, the photosphere of the sun. And so this is called the atmosphere of the sun. Even though the whole thing's made of gases, this less bright area around the sun is called the corona. The corona is the part that you can see that goes way out into space. Whenever there's an eclipse, if you see a photograph of an eclipse, what you're seeing is the ring of glowing gases beyond the surface of the sun. And so that is called the corona, and you can see that from the Earth if you have a good telescope with a good filter, especially when there's an eclipse. Now the lower atmosphere is where all those flares are going on, and it is a lot hotter there, and so that lower layer is called the chromosphere. It's quite a bit hotter. Chromosphere. So if you can imagine this thin layer around the sun, maybe I can use an orangey color for that. So thin layer close to the sun, that's the chromosphere. It's a lot hotter than the surface. And so it's all the way around the surface. And then way out into space, you'll have the corona. And so if you imagine like the lines that kids put on their diagrams of the sun, that is representing the corona, which goes way out into space. Okay, so the last feature they're going to look at with regards to the sun is what's called the solar wind. And so from those prominences and flares, the energy of many of these particles escapes the gravity of the sun. And so you get these particles going off in every direction, and they're like pieces of atoms, like electrons and protons and neutrons that aren't attached to make full atoms out of anything, but they're just a stream of these particles going off into space. We kind of can be considered living in the atmosphere of the sun because there's so much of this solar wind, which are these plasma particles going off in every direction out into space. So you can think of especially all those inner planets as being part of the atmosphere of the sun. So what happens when that solar wind reaches the Earth? Well, nothing good. Well, I shouldn't say that. If you're exposed to the solar wind, nothing good happens. So when astronauts are up in space, they're exposed to a lot more radiation than we are down here on Earth, because thankfully our Earth has a nice, strong magnetic field that protects us from a lot of the charged particle radiation that's out in space. So it has, if you could see the field lines, there would be this force out in space that is protecting us from charged particles. So when these charged particles, the solar wind comes along from outer space, from the sun, it'll get deflected by our magnetic field. It gets deflected usually towards the poles, because the Earth is a ball and it's spinning, and so some of it might end up impacting our atmosphere, especially at the poles. And when that happens, the atmosphere can kind of glow a little bit, and that's the part that is kind of cool. The places where the solar wind interacts with the ionosphere, the part of our atmosphere that has ions, it glows and gives you effects like the northern lights, or aurora borealis, the fancy word for it. And apparently down around Antarctica and Australia, you can see a southern version, the aurora australis, due to the same effect, due to that solar wind, the small amount of it that does reach our atmosphere, making parts of the atmosphere glow. So thank goodness for the protection that the atmosphere gives us, because that solar wind would be really bad for living things. It damages DNA, and it really hurts living things to be irradiated like that.